I'm Javier Conejero, and I'm going to start with the next session, which is about PyComs. But before starting, maybe you have seen in the chat that Jorge has written that a reminder for the setup instructions for the PyComs tutorial. And for those of you who haven't done or followed the instructions, it is recommended that you take a look at them and at least do the Docker pull if you are going to use Docker locally, or to download the virtual machine from the URL that we give, where... Oh, I'm not sharing. Sorry. No. No, thanks. Sorry. So sorry for this issue. So these are the instructions that you should have received in your email. Let us know those of you who haven't, and please, if you have any question, drop a message in the chat or send us an email that we will be available to help you. If you choose the virtual appliance, you will need a VirtualBox, and all the dependencies are already installed. Okay.
Since we are 10 minutes ahead of time,
should we wait?
Should we ask if people have been able to use or not?
I think it's a good question to ask them if they have questions now, because yeah, we are 5 or 6 minutes ahead.
There is a question now, what is the difference between the PyComs player and PyComs CLI?
Okay. So the question is that we previously have the PyComs player, which is was the old version, and we have just released the PyComs CLI, which comes to replace the PyComs player, including more features, like, for example, the execution in local or in cluster, with following the same interface. So we can consider PyComs player deprecated, and from now on in the next releases, we are going to use the PyComs CLI.
Maybe can you ask people?
Did anybody have any issue with the installation or Docker or something like that? Or with the virtual machine?
Somebody says that the game was not working. So I installed PyComs CLI and installed it yourself. I don't know what to install.
I see that Saurabh says on WSL, should work. Yeah, but we haven't tested. Is there anybody with any other issue? Downloading or with a virtual machine? And somebody here? Did anybody have any issue with the instructions? Okay, so maybe we can go ahead and start with the PyComs syntax session. Okay, so in this session I'm going to show you in demo how to parallelize your application with PyComs. It is oriented to show you how we do the detection of the tasks and how we work in a practical way. We have prepared a set of Jupyter notebooks, as you can see from my screen. That are oriented to tackle each of the features that we have in this tutorial. You will have afterwards, you will have access to all these Jupyter notebooks, so that if you want to take a look at them or play with them, you will be able. But for this very first session, I will drive the execution of the notebooks with some explanations. Okay, so as Daniele said before, we have a rich ecosystem based in Jupyter Notebook, but we are also able to execute Python plain scripts. But for the purpose of the tutorial, Jupyter Notebook is very good because it allows us to see it very graphical and how to deal with PyComs in a very interactive way. Okay. The other thing that we have integrated is a comms monitor here that we are able to see how PyComs is working. Okay. To start with PyComs, you have to think that we are going to execute a Python sequential code in a distributed environment. Okay. So the very first thing to consider is that we will have in this distributed environment, for this demo, we will have the classical infrastructure with a master node and some workers. Okay. During this demo and running Jupyter, by default, we have one master and 4 workers. Okay. This configuration can be modified, and in the advanced session of tomorrow, Jorge will show you how to deal with the infrastructure. But for now, just consider that we have one master node and 4 executors, which will be able to execute the tasks. Okay. So starting with the syntax, it's important to consider that PyComs is based in plain sequential Python code. Okay. So as it is plain Python sequential code, we have a library which is called PyComs Interactive. This library allows us to execute, or to, better said, to start the runtime from a Jupyter notebook. It is important to say at this point that this is not necessary in plain Python code, because if you have in Python script, sorry, because if you have a plain Python script that you're going to execute from the command line, the runtime will be started before with the launch scripts from the CLI. Okay, but when running from a Jupyter notebook, we need to explicitly start the runtime. So to start the runtime, we need to execute this ipycoms start. Okay, this ipycoms start starts the runtime with the default project and resources that will be explained tomorrow, but with default is 4 workers. And it can be tuned with a set of parameters to configure the environment. For example, we are going to start the runtime. Forget about these previous lines because they are for binder. We are going to start with graphing enable, which will provide the task dependency graph of the execution. So we will be able to see this fancy task dependency graph that have been shown. And we are going to enable the monitoring with a refresh of 1 second. This start method can be tuned with many more parameters, like for example, with debug mode, which enables to get a fine-grained logging that it is very useful to detect issues and bugs. And for example, another very useful is tracing. This will enable to generate the parameter trace of the execution that is very useful to analyze the performance of the execution. And there are many more. Okay. Once we start the runtime, we see a message here that says that the comp runtime has started with the latest version that we released a few months ago. And it says where the logs path is. Where the logs path is very important because in that folder, we will store the task dependency graph, the trace, and all the logging things that will happen during the execution. But until now, we haven't executed any Python code, user code here yet. But the runtime is started and the workers have been deployed. Okay. The third step, which is the key in the PyComp's programming model, is to import the task decorator. This is the key because we use the task decorator to define the unit of work, what is going to be the core of a task. We use the task decorator over functions that will be declared as tasks. For instance, we have here 3 tasks, square, add, and multiply, that are decorated with the add task decorator, which defines and declares them as tasks. So whenever these functions are invoked, a message will be sent to the runtime saying, hey, I want to execute this task. Then the runtime will communicate with one of the workers and will execute your task in that remote worker. Okay? So you can declare them. The task decorator allows a few parameters to tune or to give more information about the task itself. For example, it is possible to declare the return value of a task. In this case, for example, it's returning an integer. But since this is not very Pythonic, you can change it and say, I want to return 1 element. Because you know that Python can say that you can return 2 elements, for example, and this is 2 elements. Okay, so you can tune and declare. It is also interesting that if you say nothing about the returns, we have an inference. We can infer the number of returns, but whenever you give us more information in the task decorator, it allows us to boost the execution because the more information, the less work that we have to do. So, and there are other parameters that can be included in the task decorator with regard to the parameters of the function that can also be important and interesting for the task. We will see them later, but keep in mind that the key to define a task is to add the task decorator over a function and include the information related to that function into the task decorator. So we now have seen that with 3 decorators declared over these 3 functions, we have declared them. And how do we play with those tasks? With plain Python. We just invoke them as normal Python code. So we just need to call them like sequentially. It will say that he has found a task. This has let the runtime know that the user wanted to execute. It has been executed remotely. And the code has been executed in one of the workers. You can execute all of them. And it seems like it's being executed in your machine, but it is actually not. Please note here that when we call the square here, and square was declared to return an element. Okay, it returns A. And we are using A as input of the next task, as in add. This add task returns B, and we use B in multiply. Okay, So we can see very clearly in this example how the task dependencies are detected. To demonstrate this, when we stop the runtime, we can tune the stop in the runtime with synchronization, and it will get all the objects from the workers into the master node. It will retrieve everything, and you will be able to check their value. So what have we done? We have run 3 tasks in those workers, and at the end we have brought their value. And what about the task dependency graph? So as you see here, one is the output and the input of the second. The output of the second is the input of the third. Can we see it? That thing? If we go to the comps monitor, we can refresh, we can go to the execution, which will give you some information about the execution. And if we go to the complete task graph, oh, this is not okay. Okay, I think there's an issue in the monitor, in the monitor here. I think there's an issue in the task dependency graph. It should be one after the other. Okay. Oh. Okay, I have to. Okay, let me execute them all at the same. Let me execute everything again without waiting among tasks. If I go to refresh. There we go. We see the dependencies among them.
Why did you check it now?
Because I executed one by one itself, and it shouldn't be, it should have appeared this way.
It was not able to grab the objects that were generated by one task and by the other. Because the task, when he was executing the task 2, one has already finished and was not able to detect that was everything. But when you watch all the it doesn't sequentially.
Yes, but the thing what Rosa says is that when I have executed the first task, it was very, very fast, and I have waited a little bit. It executed the second one, but the first one have already finished, and it was not able the runtime to track this fast, the task dependency. In
so you mean it's like lazy execution or lazy evaluation, something like this?
Not really. I think it's a matter of the speed of the task of the dot file generation instead of
the thing is that when you run task 2, if task 1 has finished, there is no a task to get a dependency, and this is what was happening in the when you run interactively. But when you run all together, the task 1 was generated, task 2 was generated, and the dependency was detected. But in the first case, if you run task 1 and it has finished, and then you run task 2, the task 1 doesn't exist, and there is no dependency to a current task. This is why it's not printed in the monitor.
Okay, thanks, Jorge. Okay, so now I am going to the second notebook, which is synchronization. Is there any question? Any other question? Okay, so in this second notebook, I will also start the runtime. In this case, tracing is equals true, but it doesn't matter. You see that we are going to again to declare the same 3 tasks, okay? But there's an important difference here. We are going to import the comes-with-on function from PyComs because many of you may have thought, okay, this is very fun, very useful. We can execute code remotely. Okay, but the data is computed and generated remotely. How can I grab this data and bring it back to the master so that I can decide if I want to continue or I want to do something or I want to do something else? Because during the execution, the data is moved across executors, across workers, between tasks without the need to go to the master. They transfer data by themselves. But at some point, you may want to retrieve, for example, some value to detect the convergence of an algorithm, to detect if we have to stop or we have to do something else. To this end, to retrieve a data that has been generated by a task in a worker, we have the comes-with-on function. And how does this comes-with-on function work? You just need to, for example, I am going to execute these 3 tasks again, but instead of stopping the runtime, you see I have generated A, B, and C, but I want to check what's the value of C. So I want to bring it back. I'm going to add 1, and I'm going to print the value of A, B, and C. This is very interesting because we see here that A and B are future objects, and C, we have its value. This means that A and B have been computed remotely, but we don't have them in the master, okay? So these are references that we use to detect the dependencies when they are used as parameters in another tasks. So what if I want to retrieve the value of A? What was the real value? So I can call comes-with-on and bring it to the master so I can check its real value. Okay, this is one key. This is important in your algorithms because you can be executing remotely and using all the memory from the worker nodes, and you can retrieve only a small bit of data, not everything, to take decisions. So you can have tasks doing very hard computation that retrieve a very small value and then get that value to detect or to take decisions on your algorithm. If we stop the runtime with synchronization true, it will only bring back B because it's the only future object still left in the scope, and we can check all the values again. If the runtime is stopped with a synchronization, it will not retrieve the data that has been generated in the workers left in the scope. But A and B are there. So to recap, because these 2 notebooks are very important, the task definition is done with the task decorator. This is key in the PyComs programming model. And the second key thing is how to retrieve data, which is the comes-with-on function. These are the cornerstone of the programming model. Anything you want to do, we have to rely on these 2 things. Okay? Is there any question until now? Maybe in the chat.
Yes, there is one question.
Is there any question?
Well, or a comment. Dimitris says that in the previous graph, why there was a dependency between task 2 and the end.
Between task 2 and at the end. It's because
the last synchronization, you mean, or?
Yes, it's because of the last synchronization. Because we have a dependency between B and multiply, but B is still a future work, and we did the stoppage of the runtime, and it retrieved B.
Is it answering your question, Dimitri? Yes. Okay.
Okay, so if there's no more questions, please stop me if you have any question. Okay. Nothing in the chat. So I'm going to continue with 3 notebooks, extending a little bit the definition of tasks, because as you may have seen, the tasks are defined as functions decorated with the task decorator. Okay. Again, we are going to start the runtime, but it is true that the task decorator is placed on top of a function, but we are not limited to plain functions in modules. We can also decorate functions that belong to classes. Okay, so any kind of function that you can imagine and you can define in your code can be decorated with the task decorator. Okay, so for example, we are going to declare a class. It is going to declare in a different file so that we can import it and play with it. So we see here that we have the task decorator imported. We have some parameter direction. This is what I was saying before, that the task decorator can be tuned with some information about the parameters. And I will tell you why. And then you can declare your class with the functions and decorate it with the task to define which ones of them you want to declare as unit of work to be executed in the remote workers. Okay. So for example, you see here that area is a task. It returns an integer. It's a simple function. Okay. It doesn't receive any parameters, but it produces something with self X and self Y. Okay. There's perimeter, which again has the same structure, doesn't have any parameter, and it retrieves something. There's a scale size, which doesn't retrieve anything. It just scales the inner parameters of shape. And there's one last, which it's interesting to see because it has a keyword in the task decorator, which says that target direction is in. This means that this task is going to consider self as input only. Okay, as I said, the task decorator can be tuned with the function characteristics. And one of the characteristics of a function are the parameters. So you can say which directionality you want for the parameters. Okay, what are we doing in this case? If we say nothing, self, it's shape. So it will be considered as an input-output parameter because it's a modifier. You can modify yourself in Python as an object because self can be, you can call self.x or self.y. But when you say target direction equals in, you are telling us, hey, this is not an actual modifier task. This is only going to check something, but it's not going to modify the inner parameters, inner x or inner y. Okay, so this gives us that information, which is very interesting for the task dependency detection. Because if it's input, it's not a modifier, and the tasks that rely on them will not have to be executed one after the other. So whenever you have a function that you want to declare a task, you can also tune the parameters saying the directionality you want them for. If they are not defined, they will be considered as input by default, unless self, which is by default input output. Okay. And to be totally complete, if you have any other parameter here, then you could say in the same way with the name, instead of target direction, equals in. Okay, or in out. Okay, So this is the how we tune the task declaration. So we can declare our task. And now we are ready to import it and use it. Okay, so we are going to create a list with 2 shapes. And we want to call all areas. So we can call area to all of them and wait for all of them. So if we go to the comms monitor, probably this is very fast and we are not able to see the current task graph. Oh, sorry, this is not. No, it has executed all the tasks very, very quickly. We can create another rectangle, we can call the functions as we want, and we can retrieve the data with the comms_wait_on function directly, and maybe append something else and call the info shape and retrieve all parameters. What I want you to note from these last steps is that it is completely Python sequential code. The only thing that it is included here is the comms_wait_on to retrieve the parameters to check them out. But everything else, you can call the objects like normally, like invoking their functions. Then you can stop the runtime. And it will retrieve anything that it's left in the scope if you want. It's not necessary. And you can go to the comms monitor and check the task dependency graph. So this is what has detected and has happened. Note that the colors define which tasks are being executed, and the wider you see the graph, the most parallelization that we have achieved. This sync here that you see here belongs to a comms_wait_on that we have done during the execution. So it has been able to exploit and to detect parallelism in this very, very simple example. Something that I was missing here, and I want you to take into account, is that comms_wait_on seems to receive a single object that has been produced, and it retrieves the remote value to the master node. But it is not limited to that. For example, in this cell, you see that all perimeters have been appended and you have a lot of them. And you can do a comms_wait_on on a list that contains the elements that you want to retrieve. So you can retrieve more than one at the same time. Okay. And another key that it is, maybe now it's interesting to introduce, is that probably you may have said in the task declaration, hey, but what about type hinting? We are using Python 3 and this is not very Python. Okay, we understand that, but we wanted to keep the returns here for compatibility purposes with Python 2, but it is also accepted to do it this way, like in Python 3. Oh, sorry. This is also accepted. And another bit more information about PyComms is that probably many of you have noticed this comms barrier here. We have comms_wait_on, which is able to retrieve data, but for timing purposes, we have another function that waits for all the tasks that have been launched and are being executed if you want for all of them to be to wait for all of them to be executed, but not to retrieve anything. The API has some more functionalities, and all of them are documented in our documentation that you can check them out. It's in Read the Docs. But the ones that are more useful, as I say, are the task aggregator and the const wait count. To complete the definition of classes, there's something interesting that you can also exploit from Python, and it is also supported with PyComps, which is, as you may see, we can wait for many objects at the same time, but we can use a dynamic number of parameters. So in this example, which is similar to the previous one, we define the MyShaper class, but we are going to have another task here declared, which has a dynamic number of elements. The asterisk mylist defines that this function, this task, will receive an unknown number of elements on the definition. So it can be called with add all A, B, and C, or add all A, B, C, and D, or A and B. Okay, so an undefined. This is totally supported with PyComps. Okay, and you don't need to say anything in the task decorator by default. So if you declare a set of shapes, for example, 4 shapes here, and you call for one of the tasks, like the area, you wait for all the areas. The task was called add all. You can do exactly the same example as before and add all with all perimeters. Note here the asterisk that unrolls the list with a set of parameters. So if we execute it and we go to the monitor, we stop the runtime and we go to the monitor, we will see that we will have a final task that receives from all of the previous parameters. And to conclude with the definition of objects and classes, I want to introduce you the concept of a collection. Okay, something that we have seen now is that a task is a unit of work that has some inputs and produces some outputs. Okay, and the parameters of the function of the task is what we use to detect the task dependencies. Okay, so we have pieces that we use to detect and to build a task dependency graph. Something that we have included in our latest versions, I think it was from 2.8 or 7, was the concept of a collection. A collection, it's a list that we are going to keep track of the inner elements independently. Okay, if you use a list as a parameter of a task, the list will be completely used as an object itself. But if it is declared as a collection, we will keep track of all the inner elements independently. What this means? This means that you can have a list or a very big matrix composed by blocks, for example, and you want to use some blocks in one task, another blocks in another task, but you want to keep that in the same data structure. Okay, and you don't have to take care about the dependencies as using normal Python objects. The collections is just the declaration that says the runtime, hey, I want you to keep track of those elements because probably I will use them in multiple tasks, and I don't want to wrap the whole list in a single object. So for this example, I am going to declare a class again. This is a shape class, but in this case, it has some sleeps because I want to show you how it is running just during the execution, what is happening in the runtime. This shape has, again, the area, scale, size, and info shape task declared. And we are also going to consider the asterisk arcs at all. Before previous to version 2.5, we used the asterisk arcs as a collection, but it was not very useful because it only allows you one depth lists to be detected. But since we have collections, you can have lists of lists of lists, and you want to track the inner elements, and you want to keep track of whatever is happening here. So how do you declare that your list is going to be a collection and you want to keep track of those elements? It's as simple as say that the parameter name the collection, that it's a collection, and its direction. So as you may have noticed here, it can be also a collection in out or a collection out. Okay, but for the sake of this example, we are going to declare as a collection in. What this is doing is at all C, it's going to sum all elements from a collection. And we are going to have another one which adds two collections and retrieves both at the same time. Okay. We are going to declare a final one, which is a collection input-output, which is a modifier of all the elements of my list, and it's going to scale with the value passed as a parameters. Okay. So now that we have declared the task with the number of returns and the characteristics of the parameters, that we can use them as normal Python. We can declare a set of shapes in this case, and we are going to calculate all the areas. Let's synchronize the results. And now it's taking a second or two because this hasn't got any example. And we can do some more computation, calculating the area of one shape. But when we go to collections, then we can use the list without asterisk, like here. If we want to use the previous version with asterisk arc, we are forced to use the asterisk to unroll the list. But this is not necessary with collections. If you want to access to collections, it is exactly like Python code that you invoke, but with two lists. And during the execution, you can go to the monitor quickly. Now it's doing some computation, so we can go to the current task graph and we see that it is running task number 23. And it's taking a little bit and it has finished. So it's quite fast in this example, but what you can see here in the conf monitor is the execution while it is being executed. Once finished, it is not running anymore, and you have to wait for the execution to finish. If we call again, let me see if I can do it quickly. Current task graph. it has finished. Oh. So once it is stopped, you can check the complete task graph. And you see that it has been able to extract the parallelism. Is there a question?
There is a question from Asier, but I think it was from the first notebook. I don't know why we received later the message. Asier, I don't know if you want to ask Hadi directly.
Yeah, I can do that. Thank you. Yeah, I was asking if you could explain a little more in detail, basically this graph. I was asking in the first example, which was the simplest one, but yeah, I couldn't really understand what it was being parallelized. So if you could explain that a little bit, that would be helpful. Thank you.
Do you mean in the very first example, in the very first notebook?
Yes, I mean, I have doubts in all of them, but I think that the very first one would be the simplest one to understand.
Okay. Okay, look at, yeah. If I go to the first one, which is this one, and I'm going to split this. Oh, I cannot split the screen. If I go to this one, which is synchronization and happened this, invoking tasks. Maybe this is more clear.
The question is, which task was able to parallelize? But in fact, no first task.
No. In this example, there was no any parallelization in this example, in the very first notebook. What we see here in the task dependency graph are the tasks that force to execute one after the other. So we see that there's the very first task returns A. It creates, there's a dependency between square and add, which is A, and this is D1, B1 here. Okay, so, and there's between add and multiply, there's B, and that's why there's D2, B2. Okay, the other arrows belong to the synchronization at the end of the execution. Okay, but if we go to a more complex task dependency graph, like this one, which is for the last example. This is not with collections here, and we go to, for example, the last step, accessing to collection, scattering data from a collection. We say here that, sorry, let me check the monitor. The red ones are perimeter and the odd all C. This example, I think it's more clear. Here you see that there are 5 add perimeters, and there's one add all C here. And you see that it has been able to parallelize. If we go to the code, this piece of the code corresponds to this cell number 15. So we have executed all perimeters here, like in a loop, but the runtime has been able to detect that there's no dependency among them. But when we called add all C, which is a collection input, it received all elements stored in perimeters and add add all of them in a single one. So detected that there's a dependency between all of them into this task. So at this point, this loop that seems sequential here, it happened to be parallelized completely in parallel because there's no dependency among them. And whenever we called add all C, it waited for all of them to finish so that it can add all the results in the same place.
Okay, that's useful. Thank you.
That's a good question. Okay. Is there any other question?
Not now.
Okay, so I'm going to continue with the next notebook, which is for files. Okay, so up to now we have seen how to declare tasks, how to synchronize data, and how to deal with classes and collections. Okay, but we are aware that many of you in your algorithms, you play with files. You probably need some data sets or something that belongs from another application, and you need to use a file into a task. Since the tasks are executed in a remote worker, you can declare that a parameter is a file so that the runtime is aware of that, and it will transfer the file to the worker node so that the task is executed with the appropriate parameters and files. So if we start the runtime again, you will see here that we can import the task decorator, but parameter library allows you to import file in, file and file in out. These are the configuration for the parameters to allow us to know what your task parameter files are going to be executed. So if we declare, for example, we have 3 tasks here, one for writing a file. So it is going to create a file. So we define it as a file out. Note that this is a string with the path of that file, and it will create that in that place. We will handle that file to connect and to do all the piping with the dependencies among tasks. We are going to do a second task, which is append, which declares that it is going to have a file input output. So we can consider this task is a modifier. It retrieves something, adds something to the file and closes it. And one last task, which is for reading a file. So this is an input file. It just opens, reads the content and retrieves the content. This is a very simple example, but in your case, you can consider that a file is, as I said, a data set or something belonging to another application that has been produced. So you can invoke as normal functions, Python functions, but the difference with the objects is that those parameters are strings that identify the files. So it can be paths or file names. Okay, so if we call for the very first task with my file, it will write the content into a file called my file that it's going to be somewhere in the worker. Then we will call to append that we will add something and we will read the file. Okay, so we see that there's a task producing something, another one which is modifying, and the last one which is reading. And finally, we are going to append something else. Note here that the dependency, if we focus a little bit, it's from write to append to read. But whenever we execute also append, this read file and this append can be executed completely in parallel because read file is input and append is input output. Okay, so this read file is not modifier. So it's going to read this at this point. But this can be executed because this version we have here. So if I execute it very quickly and I wait for the values, And I go to the monitor. Hopefully, let me stop the runtime. I thought that had stopped. If we see the complete task graph, you see that it has written the file, it has appended, and it has been able to extract the parallelism from reading and appending. And these tasks have been executed in parallel. This is quite similar to the question that you did before. Okay. Any question with files?
No, there are no questions.
So I'm going to be very, sorry?
There are no questions in the chat. So
okay, so I'm going to be very quick with these last two notebooks. To end up with this session, which is the usage of constraints. Okay, so all tasks are executed considering a set of resources, but you are also able to define that your task, for example, wants to use multiple cores. Like Daniela said before, you can have, for example, internal parallelism within a task, like, for example, using OpenMP or using MPI or whatever within your task. But a task, by definition, has the default value of 1 core. What if you want to declare that your task is going to use multiple cores, for example, 2? If you are used to use NumPy, for example, you know that it can be parallelized internally with MKL or BLAS or other libraries. So maybe you want to exploit the inner parallelism of any function internally. This declaration is very simple with PyComps because you only need to add another decorator on top of the task decorator, which is add constraint decorator, and add the characteristics that you want for that task. The most common is to declare the number of computing units. Like in this case, I want Square to use 2 computing units, which means 2 cores, or 1, which is the default for add, or I want to use 4 cores for the multiply task. This means that the runtime is going to respect this usage, and we will see later in the next session that we will see tracing, that we will see that the runtime respects all these slots. So in this machine that we are executing now, we have 4 cores by default. Okay, so it will be able to execute 2 squares at the same time, but no more because they have 2 cores by default. And it will be able to execute 4 adds at the same time, but multiplies only 1. Okay, and we will see that later in the trace. Something interesting here is that the constraints are not limited to the number of cores. There are a lot of parameters that you can tune. For example, you want to execute in a node where there's a particular software configured, or I want this task to be deployed in a worker with a GPU. Imagine that you are using some kind of library doing some computation in GPUs, and that task requires a GPU. You can declare the GPU or the number of GPUs that are required for that task. And the runtime will take that into account. For example, if you execute in an heterogeneous environment. And to end up with the session very quickly, the constraints can be very useful to tune or to define the characteristics of your task, but we have another decorator, which is an implement, the implement decorator, which allows you to define multiple times the same tasks, but with different constraints, and let the runtime choose which task is more suitable for a particular node at a particular point of time. So if you have, for example, in this example, we have one task which is done, adding two lists using plain Python code, and another one which has add two vectors with NumPy with 4 cores. It is using the internal functions of NumPy, which are internally parallelized. So whenever you call to add two vectors, the runtime will also choose the most appropriate in that moment. And if he sees that it is better to choose and to execute add two vectors with NumPy, it will do, and you will only need to invoke add two vectors. So the runtime is able to swap. The only thing that you can take into account is that the output has to be exactly the same for all the implementations in this case, okay? And I think that, just to mention, there are many other decorators for execution, for example, to execute binaries. If you want to execute, to declare that a task is going to be considered as a binary or an MPI or an OpenMP, there are many other decorators that you can check in read the docs, which is icons. And you can check them all here. In application development, binding, model, and test definition. You have here. So it's in other task types. So we have plenty of them here. And I think that with this, we end up with this session, and we will have a short breakup, and we will continue later with the hands-on. So please take in mind to follow the instructions and download the virtual machine or the container, and see you at what time? In 15 minutes. No, it's 20 minutes. In 20 minutes. Welcome back to the programming distributed computing platforms with comms tutorial. In this third session, we are going to continue with a PyComps hands-on, so that you can use the notebooks that we have been used in the previous session and play a little bit with PyComps by yourself. The first thing is, the first step to start with this session is to start VirtualBox and the virtual machine if you have chosen this method. Please remember that the user is comms and the password is set here, and open a console. And for those of you who are going to use without virtual machine, please remember to install the PyComps CLI. And let's start with the tutorial. I'm going to guide you with the steps. Okay. So the first thing is to start the virtual machine. I have go to VirtualBox, for example, and run it. No? On this? Ah, there's lights. I have to Share. Clone https://.com. Tutorial apps. And this will download the latest version of the notebooks that you need to do this tutorial. Then the next step is to go into tutorial apps folder. And here now you can do the init, the PyComs init. No, it's exactly the same, but the difference is that you have the folder with the latest version of the notebooks. We updated. Yes, it is linked. When you start the Docker, it is linked to the folder where you are in at that moment. And then when you start Jupyter, it starts from that particular folder. Because it has to be something like PyComs monitor start. It has to be something like this. Is this your output?
Okay, I think I now get that. Yeah, okay. I think I know what happened.
Try to use the IP instead of the host name.
Okay, yeah, you can use here localhost, you mean. So now, again, the username is root. And then the next step is to do PyComs Jupyter. This will start the service of Jupyter within the Docker container, and it will also drop you an URL, which is listed here. So you can click on it and it will open the Docker. So at this point, you should have in your web browser, you should have in one side, the comms monitor, and in another tag, the Jupyter. Okay, so the next step is to go into the Python folder. This tutorial apps contains all the applications for all languages supported by PyComs, C, Java, and Python. But in this section, we will focus into the Python folder. Here you will see that there are many folders with applications that are plain Python, but we are going to go to the notebooks folder. And here, now we go to hands-on. Okay. Now, click in the number 8, sort by key, Jupyter Notebook. Okay, this is the very first notebook for these sessions. This is a real application which is aimed at sorting by key a random data set. For example, the previous notebooks that you have seen were only small snippets to show you how to parallelize small pieces of code. But now this application is real. So what we are going to do, first of all, is to create a data set. So we are going to define a function that generates a random set of files with random data. Okay, so we declare, and now we create those files. For example, number of files, let's say 4 files. Number of pairs, how many pairs, random pairs, let's say 20. And the directory name, my data set. You can tune the number of files and number of pairs as you want. Please do not include a very high number here. Now it has created 4 files with 20 pairs. And we can see how they have been created. Okay, so now we have our initial data set. And let's start with the algorithm. First of all, import the PyComs library and start the PyComs runtime. You may see here that the graph is true and monitor is also enabled. So once you start the runtime here, now you can go to the comms monitor, click in refresh, and it will appear interactive mode 01. If this is very small, refresh the entire web page, it will appear larger. Okay, so now we see that localhost is green, running with 4 executors, 4 workers. Okay, it is still empty. We will see later. Now, import the task decorator. So you just need to click in run this cell, and let's define the very first task, which is sort partition. This function retrieves, has the input a single file containing the data, and it internally reads that file and sorts the contents and retrieves an object with the contents sorted. Okay, so we declare that function and that task. And we are going to declare another task, which is called reduce task, which is aimed at taking 2 sorted data sets and sort them in a single one. So pick 2 and give an output with the merged value. Here you can see that there's a special parameter in the task decorator, which is called priority. This allows the runtime to know that you want to execute this task as soon as possible, if possible. But it doesn't break any data dependency. Data dependencies are the most important. And as far as it is possible, the scheduler will try to make them in advance. Okay, let's run it. And then we are going to declare a helper function, which is merge reduce, which will go doing a merging of 2 by 2 in an inverted tree, in a binary tree. It is very simple. It creates a queue and it takes the 2 from the queue, and the result it's appended at the end. Now let's go to the main application. So the main application, it will take the data set, it will call to the sort partition task with each file, retrieves the output and stores in partial sorted, and then it calls to merge reduce helper function, which is calling the reduce task. So if you execute this code, it will say something like this. It will retrieve the output, the sorted output. Okay. If you execute the stop, then you will be able to go to the monitor and check some information about, for example, the average execution time, or as said in the previous session, the complete task graph. Okay, since we have 4 files, it has been able to sort these 4 files completely in parallel, but the merging has been done 2 by 2 and at the end. Okay, so what we can extract from here, the lesson that we learned is that if we have 4 cores, the sort partitions have been executed completely in parallel, and then as soon as the results have been produced, task number 5 and 6 are also being able to be executed parallel, and number 7 has to wait for all of them to finish to complete the execution. So this is a very, very simple example of like a map reduce sample. Okay, if you have been able to run this notebook, then you can move on to the next one, which is the k-means with reduction. Number 9, k-means with the reduced chunks. This is a more complicated algorithm which tries to cluster a set of points, of 2 dimensions or multi-dimensional points in a set of clusters which belong to the closest center. Okay, it is trying to find the center closest to the predefined clusters. What we want to show you here is that you can define and you can execute again this cell by cell, start the runtime again. What we want to show you here is that you can do your very complex algorithms in a very simple way and parallelize them very simple. The thing that you have to take into account is to define the units of work as tasks. And for example, in the k-means, we are going to start with some functions to generate the initial data set, because it's necessary to start the algorithm. And we are going to define, for example, a function that calculates the minimal distance between all points of a fragment to all centers. Another one that calculates the partial sum of all of them to that center. And we need another reduction function which accumulates all those distances, because it is necessary to calculate the distance in order to check the convergence of the k-means algorithm. Okay. Of course, since it is an iterative algorithm that keeps checking the distance, if it has been achieved, we need to declare the has converged function. And I want you to notice that until now, we have only added 2 lines here. The task decorator, no, 3 lines here. The task decorator for cluster points partial, the task decorator for partial sum, and the task decoration for the reduction center task. Okay, nothing else. If we continue with the notebook, now we have a very long function which is for plotting purposes. So this is just will show you a very fancy output, and we will have the main execution. Here we will see that we can integrate it also with snippets, with Jupyter Notebook snippets, so that if you click in run, it will show you like a fancy menu that you can tune with the parameters that you want to use for running your k-means. If you run it by default with the given parameters, it will start running, iterating, and it will drop you the results per iteration until it reaches a distance lower than the given epsilon. If you go into your monitor quickly and refresh during the execution, I think I will not arrive. We go into interactive mode and current task graph, you will probably see this, that it is running, and there are a few tasks running. Some of them are assigned, some of them pending. And this is more or less what the runtime is doing, or more or less, no, it's exactly what the runtime is doing inside with the tasks and its management. You can run, sorry?
Yeah, just because there are some people that with the problems are a little bit lost. If you can show
Yes.
again how to reach this this notebook.
To reach the monitor?
No, the notebook.
Oh, the notebook. Okay. If you go back and you go to okay, the browser URL, when you start I'm going backwards. When you execute PyCom's monitor start, it will drop you an URL here. This is the URL, open the monitor. And the one for Jupyter, once you execute PyCom's Jupyter, it is dropped here. Once you open Jupyter, you have to be in tutorial apps. Then you go into Python, notebooks, and syntax. Sorry, and hands-on. Sorry. And these are the notebooks that we are using in this session.
And you are now in the 9 k-means, right?
In the name k-means, exactly.
There you will get at the same point.
You will get this example. So if you execute the notebook until running the example, you see that the output of the k-means, and now you are ready to stop the runtime if you don't want to run k-means anymore. Once you execute the stop and the runtime is stopped, then you can go to the monitor, in interactive mode, to the execution, go to the complete task graph, and you will see here that what has happened during the execution, and you see clearly all the iterations. So the blue tasks are the clustering task, the white ones are the partial sum, and the red ones are for the merging. So, and you will see that it is spawning a lot of tasks and doing this map reduce iteratively until it converges as regards 17 iterations at the end. Okay. There's another k-means notebook that you can execute it again, but this has one important difference with the other one, with the previous one, which is the reduction phase. Okay, so if you, let's see how this one behaves, because in this one we have defined a different reduction algorithm. If you execute it with the default parameters, then you can go to the comms monitor, refresh. In this case, mine is interactive mode 3. Yours it will be last one. You can see how it is behaving during the execution. And once it finishes here, it will show you the output. The distance is increasing. Yeah, the distance is 0. It has converted. The result is exactly the same that in the previous execution. And if we stop the runtime, now we will be able to check the complete task graph. So if we compare, this is 2 by 2, and the previous execution, task graph, did 4 by 4. Okay, do you see the difference? So depending on the way that your algorithm is done, we are able to extract automatically the parallelism. So the key here is that you can do your algorithm, parallelize, and it is good to do an iteration, check the trace and the task dependency graph to see if there's something that can be improved. Is there any question until now? Yes. That is, there is no application. You need to click and refresh here. Once you start the runtime, you need to click and refresh so that you can see here the number one. Otherwise, if it is very small, you can refresh the whole monitor and all of them will appear here on the left side. But to appear here, the runtime must have been started. Okay. It is a good practice when you open multiple notebooks to shoot down some of them that you're not going to use by clicking on these boxes, the red ones, and clicking in shoot down. Okay. And now, before giving you an exercise, I want to show you number 10 Cholesky, which is a known factorization decomposition of the triangular matrix algorithm, which can be easily parallelized with PyComps by defining the common operations over Cholesky with a task decorator. So if you, again, start the runtime, import the necessary linear algorithms from SciPy, or in this case, we will declare the task that we need for creating a block. We need input data set and the Cholesky usual functions, hot array, solve triangular, ggem, and some auxiliary functions for the matrix and the blocking. And then we have our main code. This code runs to Cholesky, calling those functions that have been declared as tasks, again with the code widgets. Run it. You can choose the matrix size and the block size. So it's 8 blocks by 8 blocks of 124 per 124 elements, and the number of MKL threads. So if you run, this is very fast. It has been executed very, very fast. But the interesting thing here that we want to point out is that no matter that your algorithm is, we will try to do our best with the minimal impact on your code to extract the maximum parallelism. And this code is especially interesting because the task dependency graph that is generated shows that very good. Let's see. Okay, now. So here you see the task dependency graph that has been generated. So to recap, the thing that we have done to this Cholesky algorithm is to split it into functions, to add the task decorator, and at the end, one comes later. So this is for you to this is a very graphical example. Okay, so now it's time for you to play a little bit, and we have prepared we have prepared a workout exercise. It's very simple, but we want you to play a little bit with PyComs to see if you are able to solve this small exercise. It is composed by a set of documents, a set of files, which are plain files. And the idea is to read them and merge all the appearances of each word in each document for the entire set of documents at the end. Okay? So if you go into the notebook, which is called 11 word count exercise, we have prepared the code, the sequential code that does a word counting. Okay? What we want you to do is to try to parallelize this Python code, considering the things that you can get from other notebooks, and we have shown here. So we will give you some minutes to do this exercise. And let us know if you have any question or any issue, and we will try our best to help you. Okay, how is it going? Have you been able to parallelize this exercise? With the given data set, what is the parallelism that you have achieved? Okay, let's solve the exercise step by step so that you can check with your solution to see how, if it works the same or you have something different. Okay, so the first thing is to add some cells here and import PyComs interactive as, for example, as ePyComs. The second step is to start the runtime. PyComs. So let's run the first one. PyComs.start, and let's say that we can the graph equals true, monitor equals 1000 for refreshing rate. Okay. Now we have a runtime running and it's interactive mode 0.5. If you go to coms monitor and refresh, now it should have appeared here, but there's nothing running. Okay. The third step is to import the task decorator. So from pycoms.api task import task. And since we are going to deal with files, we will need probably the file parameter from pycoms.api.parameter import file. Which direction? Since we are going to read files, only read from a data set, we will need file in. Okay, so now we are going to need the import OS because we are going to use the built-in library to read files. Okay. So now we have here a function. Let's first start for analyzing the code to see what's happening here. There's a function for reading a single file and retrieving its content. It reads the file and splits the line. There's another function which does word counting over a dictionary. No, sorry. It goes through a set of words and creates a dictionary of appearances. To this end, it creates a dictionary, and for each entry, if it exists in the dictionary, it increases by 1, and if not exists, it creates an entry in the dictionary with value 1. Okay, so we have a reader, a word counting for a list of words, and then we have another function which is merge to dicts, which does the accumulation of 2 dictionaries of words with their appearances. To this end, it iterates over the second dictionary, and if that key exists in dictionary 1, appends all appearances of dictionary 2, and if it doesn't exist, it appends the number of appearances. Now we go to the main. What it is doing here is it takes the dataset path, there's a folder where there are a set of files, and then iterates over the files in the dataset, creates the dataset path, the absolute path, and calls to read file per file. So there's a for loop, reading files, and then calls to word count with the data retrieved for that file, and it is appending in partial result. Okay. At the end, with all those partial results, it loops again, merging 2 dictionaries. Well, now we can see that we can define the read file as a task. First, we have to think what it is file path. It's going to be a file. So file path has to be file in. And does it return something this task? Yes, it returns a list of words. So returns equals list. It's a list of words. This is also compatible with returns 1 element, which is a list of words. Now we have another function, which is does the word counting for that data. So this can also be defined as a task. And in this case, the input is data, so it's not necessary to define anything, and it is returning something. So returns, in this case, we can say 1, or it is returning a dictionary. So it's the same. And then there's another function, which is merge to dicts, that we can also define it as a task. So the dict1 and dict2 are input dictionaries, so there's no need to define it here, and there's a return, so we can say returns equals dict again. Okay, now we have our task defined, but if we go to the main code, let's see what happens. Let's run this cell, run this cell, and run the algorithm. Hey, something happened. There's an error, unexpected error. Wow, there's a typo. I did it wrong. In merge to dict. So let's fix it. Again. Well, it has done something. Okay. But let's print the results. Another error. What kind of error is this? Future object has no attribute values. Okay, this means that we are trying to print something that is a future object. So at this point, we need to retrieve that data. So what it is missing here is to PyComs.api import wait on, and then retrieve result equals wait on. And now we run it again, has actually retrieved data, and we can see the expected result. At the end, the last step to complete the exercise is to stop the runtime by PyComs.stop. And in this particular case, we don't need to synchronize anything because it's not necessary. We will check if any issue happened. And now we can go to the monitor, refresh, and see what happens. There you go. We have executed it twice because we failed the first time printing. So we see that the blue tasks correspond to data generation, the white ones to the word counting, and the red ones to the merge to dictionaries. Okay, do you have any question? With the exercise, do you have any issue or any?
I've got a question, Javi. So you've explained earlier what's the importance of file in and file out, but I don't quite understand because in this case, does it change the parallelization or anything if you don't specify that the input file is a file in, or there's no difference in this case?
In this case, it is important because what you are saying here is that this task is going to receive a file. It's not going to produce nor modify. So this is consuming that file, simple. If you have another application that generates a file, then you should put file out because it means that that parameter is produced by that task.
Okay, and what does that change? That changes the graph, or is it something internal in comms?
It may change the graph. The directionality may change the graph if, for example, the same file is used multiple times. Okay. For example, if you use the same file within multiple tasks and they are filing, they will be completely parallel. But if you use the same file and it is declared as file in out, since they are modifier, it will have to respect the first task, then the second, and the third, because they are modifiers and there's a dependency one after the other, input output.
Okay, thank you.
Is there any other question? Okay, so for you that have been able to deploy the Jupyter Notebook and the monitor and so on, there are two solutions for the word counting. One, which is the one that I have just done, and you will see exactly the same. But there's also another solution with a reduction like in an inverted tree that you can execute it if you want to compare the results of the graph. Okay. To wrap up, before going for lunch, please consider that it's not good to have many notebooks at the same time open. So shoot down the ones that you don't want. And if you go into the notebooks folder here, you will find the hands-on that we have been working on, but in the syntax folder, you will find out all the notebooks that I've been using earlier, okay? With this, I think I will give you the last step, which is how to stop safely the environment. To stop safely the environment, you have to go to the, you have to close the web browser. Then you go to the console and do Control-C. Okay. The next step is to do PyComs monitor stop. So we have first closed Jupyter with Control-C, then we stop the monitor, and then you can clean up everything, or you can keep it for later. The command for clean everything, for cleaning the Docker instance is the one that has been said before, for those of you who had issues. Okay. If you want to restart again, please go back to the initial of the instructions, and then you will have to do the init again. Okay. So